Welcome to Chapter 11, Balanced Search Trees. A plain binary search tree works well on random data, but sorted data stretches it into a long line and search slows down. A self-balancing tree keeps its height small, so search, insert, and delete all stay big, O of log n. Let's start with why we even need balanced trees. We will watch a normal binary search tree break on the most common kind of input. In Chapter 10, you built a binary search tree, and it gave you big O of log n search. Now let's feed it the kind of data that shows up all the time. This time the data arrives already sorted. That is very common in real programs. Think of user IDs in sign-up order, timestamps, or a sorted export. The keys come in as 1, 2, 3, 4, 5, and so on. We insert each key with the plain binary search tree rule. A bigger key goes to the right. And now the problem. Every new key is larger than everything already in the tree, so it always turns right. Let's watch what shape that builds. Let's insert 1, 2, 3, and so on up to 7 all in order. We start with 1, 2, 3. Each bigger key goes to the right, so a staircase is forming. Now we go up to 5. That is 5 nodes and the height is already 4. This does not look like a tree anymore. And with all 7 keys, we get a straight diagonal. Every node has only a right child and no left child at all. This is really a linked list built out of a tree's struct. So the height now equals n to search for 7. You walk all 7 nodes. That is the same slow scan a plain array or linked list would cost. With 7 sorted keys, the tree height is 6, and search is big O of n. With 1 million sorted keys, the height is almost 1 million, and search is still big O of n. With 1 billion sorted keys, the tree is a billion deep, and a search takes a billion steps. So a billion sorted inserts give a billion deep tree, and search is a billion steps. The tree has all these pointers, and it still works exactly like the linked list we wanted to beat. We kept the ordering rule, but we lost control of the shape. The binary search tree rule was never wrong. We just never controlled the shape. A self-balancing tree adds 1 repair step. After each insert, if a subtree got too tall, it rotates to level it. This keeps the height at big O of log and no matter what order the keys come in. AVL is the strictest rule. We build it and trace it fully in this chapter. Red-black trees and B trees are looser or wider cousins. We compare them here too. A rotation keeps the binary search tree order. It only changes the shape, never the order. And now the guarantee. An AVL tree always keeps its height at most about 1.44 times log n, so a billion keys give about 44 levels in the worst case, not a billion. Every operation stays big, O of log n, whatever order the keys arrive in. Let's look at what you will be able to do by the end of this chapter. First, you will compute a balance factor. That is the height of the left subtree minus the height of the right subtree for any marked node. Second, you will pick the correct rotation. You will tell the 4 cases apart, given an imbalance. Third, you will trace an AVL insertion. You insert the key, update the heights, detect the imbalance, and rotate. Fourth, you will compare, not implement. You will place red-black trees and B trees on the same trade-off map. One idea drives the whole chapter. A rotation restores height balance without breaking binary search tree order. In Chapter 10, big O of log n held only when the tree stayed balanced. Balance makes it a guarantee, even on the sorted input you just watched. Let's build an easy picture for balance. Think of a seesaw. It levels only when the two sides carry close to equal weight. Load one side too heavy, and it tilts to the ground. To level it, you do not remove the load. You shift one weight across the pivot to the lighter side. One small move at the pivot, and both sides balance again. Every node in the tree is a tiny seesaw. Its left subtree sits on one side and its right subtree sits on the other. When one side grows too tall, the node tilts. A rotation shifts a node across that pivot to level it again. Now watch where this picture breaks down. A seesaw balances two whole sides at once. A tree rotation is more precise. It relinks exactly 3 specific nodes, and it must also keep the binary search tree order, not just even out the weight. Let's try a second picture for the same idea. Think of a hanging mobile sculpture. It stays level only if each arm's weight is close to its siblings. Hang a heavy shape on one arm, and the whole mobile tips. The fix is not to remove the shape. It is to rehang one piece. A small local adjustment restores level, and the same shapes still hang. A search tree is a mobile turned sideways. Each node is a joint, and each subtree is an arm. If one arm grows much taller than its sibling, the tree tips and search along the tall arm slows down. A rotation rehangs the piece to level it. It is rehung, not rebuilt. Watch the limit again. The mobile rehangs a whole arm. A rotation only relinks 3 specific nodes. And unlike a mobile, it must keep the order left is less than node. Node is less than right while it does so.